Okay, and full slide. Okay, is it possible to see my slides?
Yes.
Okay, so I will start. So good morning, my name is Dmitry Semenok, and today I will present my final project within this course, Advanced Materials Modeling, and the project is dedicated to strontium doped molecular hydrogen. This topic is closely related to transitions, phase transitions in compressed molecular hydrogen, which were intensively studied for maybe last 20 years, experimentally and theoretically. And as you can see on the diagram on the right part of the slide, the pure molecular hydrogen undergoes several phase transitions at room temperature and below room temperature through several phase modifications, phase 1, 2, 3, 4, and 5. And as it was observed in 2017 by Diaz Silveira, Ranga Diaz and Isaac Silveira, it's published in Science, we even can observe at about 500 GPa, 5 million atmosphere, transition of insulating molecular hydrogen to metallic atomic state. And they observed that initially transparent hydrogen sample compressed to 2200 GPa, under compression becomes opaque, and after that even reflective. So one of the phase modification, phase 4, is given at the slide here at the bottom of the slide, and you see that the hydrogen molecules start to interact and dissociate and form the H3, 3 hydrogen molecules, and even benzene-like or graphene-like hexagons, graphene-like hexagons. So some aggregates, so something happens, and this compound becomes opaque, and after that even demonstrate the semi-metallic, semiconducting, and later metallic, even metallic properties. Okay, this research is closely related to experimental techniques, to compression of matter on diamond anvil cells and diamond anvil cells on diamond anvils, and synchrotron research under high pressure. And this work has been done in collaboration with Jilin University several years ago. So I will follow and first describe the methodology that the chemists use to investigate new phases, formation of new phases under extreme pressures, from theoretical point of view, of course. The first step is structure search. In this work, I used the USPEX search for stable crystal modification for stable structures in the strontium hydrogen systems. And we search structures with minimum enthalpy at the series of pressures 50, 100, 150, 200 GPa. This series of pressures cover the experimental range where the system was investigated. So USPEX generated about 10,000 or maybe more structures, different strontium hydrides, ordered by enthalpy of formation. And after that, we can construct a so-called convex hull, where the points of this convex hull are the most stable, thermodynamically most stable phases. About 5 years ago, the people thought that this is the last step, and actually this set of phases is really set of phases that should be experimentally observed. But in fact, it's completely wrong. And a lot of rubbish, trash papers were published, hundreds and hundreds, with prediction, even in these systems, strontium hydrides, where the people, theorists, predicted existence of phases which in experiment cannot be observed at all. So typically this step doesn't work, and we need to use some script that generates and uses, investigate all set of generated structure biospecs, all 10,000 structures. And after that, this script just predicts the X-ray diffraction pattern. And after that, we can automatically compare it with experimental results. So by this way, we can find, probably we can find structures that can help us to explain the experimental results and determine new phases that formed in the diamond angle cells. Okay, it was implemented for USPEX by Michele Gallas in 2019. And in a bad case, no good structures found. It means that we need to create the supercell and take into consideration more atoms in the structural search on the USPEX at the USPEX step. It's typically a serious complication. In most cases, we even cannot overcome it. It's just let's be optimistic. There is a wonderful example. Just recently in Nature was published a room temperature superconductivity in the carbon-containing sulfur hydride. And according to many research, it cannot be found by USPEX search. It cannot be found by any other evolutionary algorithm because this compound just metastable. The authors didn't use heat, and they synthesized something which can be described as an organic crystal containing carbon and sulfur and hydrogen, but it's metastable, very far from convex hull, and cannot be determined, cannot be found using common scheme for inorganic materials that we use that I described. But let's be optimistic and let's imagine that structure has been found. Next steps are following. It's a calculation of band structure. If we know that this is metal or semiconductor or insulator, we can compare it with optical transmittance, which can be obtained from experimental data. We can also calculate the phonon spectra and check the dynamical stability of these compounds and the equation of states at different pressures. We can calculate the cell parameters, ABC and volume of the cell and compare it with experimental data that typically we have from X-ray diffraction data. So let's proceed with strontium hydrides. And as I described on the previous slide, we performed the USPEX calculations at several pressures. Here I gave just the pictures for 50 GPa and 100 GPa. And the main conclusion that we can extract from work with USPEX is that the convex hull construction is not effective when we're close to the pure hydrogen or close to pure metal. There are a lot of phases, which is given on the left bottom picture, left bottom diagram here. There are a lot of different phases of different strontium hydrides, which are very close to convex hull, and even small contribution from, let's say, anharmonic contribution or ZPE energy or enthalpy factor, finite temperatures, impurities, defects, and so on, and distortions, non-hydrostatic conditions. All of these factors together and separately can completely change the situation on the convex hull, and we don't know exactly what we will observe. So we have to investigate not 10 structure, but let's say 100, 200, 300 structures, which lies in a layer, with thickness about 100 milli-electron volts above the convex hull. They are formally metastable, but due to some reasons, we don't know which exactly, they may become stable and appear in experiment. Okay, this is experimental X-ray diffraction, just one experiment, one diamond cell out of 7. And the experiment has been done within the interval, from 70 to 146 GPa. You see on the diagram B, in the picture B, you see the series of X-ray diffraction patterns. And according to our opinion, current opinion, it's a mixture of two phases. One of the phases can be directly found by USPEX, directly found in a convex hull, built on the basis of USPEX results. It's a strontium H22 with P1, but actual structure is tetragonal, so the tetragonal structure and very simple X-ray diffraction pattern, just a few peaks. The first peak is about 8.5, next peak, and the next series, it's of course distorted structures. That's why there are several reflections just merged together. Very simple pattern, which is common for cubic actually crystals. And the second phase, as we think, is a strontium 3H13. It's a monoclinic phase, which cannot be found in the convex hull. Okay. So let me describe in details the phase 1. It's a monoclinic strontium-free H13. It's the first time that we discovered such the phase with such composition. And I do not know any examples with such structure in the references and literature. In hydrides, no, I do not know that hydrides with such composition were synthesized before. So at 150 GPa, at the highest point of our experiment, we see that this structure is actually placed in plus 60 milli-electron volts from the convex hull. So formally, it's thermodynamically unstable. And as I said, it's 5 years ago. No one will, of course, consider this structure, and they just will put it in the garbage bin. But now we can compare this structure with the experiment and see that there is actually not bad agreement with theoretically predicted X-ray diffraction peaks, position of this X-ray diffraction peaks, and experimentally observed X-ray diffraction patterns. Moreover, when we calculated using the phonopy and PBHJ approach, using the WASP and the phonopy Python codes, band structure, phonon band structure, and phonon density of states, we saw that actually this compound is dynamically stable. So we can continue work with it. And we also compared the volume predicted using DFT methods volume, the same functional as PBE into GA, and the experimentally observed. It's a points, it's a circles here, red and blue circles, and the theoretical volume of unit cell is just black, this black line. And as you see, as you can see, it's a quite good agreement. At low pressures, the compound probably loses some hydrogen, becomes the content of hydrogen becomes less. That's why there is some deviation, and the experimental volume is lower than theoretically predicted. And let me see we also calculated the band structure, electron band structure of this compound, and we saw a lot of bands, electron bands that just cross Fermi level. So compound demonstrate the metallic properties, and I also will pay attention on the diagram B in the right bottom corner of the slide, where we compared also ABC parameters, cell parameters, unit cell parameters with the experimental ones, and you see that the circles, blue and red circles, are very close to theoretically predicted parameters of the unit cell. The structure of this compound is interesting because it contains zigzag H5 molecules with almost the same distance between neighbor hydrogens. It's close to 1 angstrom between hydrogen atoms. It's close to distance between hydrogen atoms in pure H2, compressed H2 and H2 molecules. And also it contains some H3 fragments, which is hydrogen molecule associated with atomic hydrogen. No, we can describe it in this manner. Probably it's annuals. We didn't calculate the charge distribution there. It's a future task. And we can prepare some kind of quiz in order to determine how this phase is, can this phase be used to explain experimental results or cannot. Complication in this case that this is mixture of the phases, so we can some of the XRD peaks may overlap, and we maybe cannot we do not know how they overlap, and sometimes there is a probability to make a mistake in interpretation. Okay, it's thermodynamically unstable formally. That's a plus 60 milli-electron volts from thermodynamical stability line from convex hull. But XRD corresponds to experiments. Yes, it's dynamically stable. Yes, and the equation of state and all cell parameters well correspond to the experiment. It's yes, and this is middle. And in experiment, you see the two pictures of the samples, and it's not transparent at all. So it's a, let's say, positive sign that this is really not insulator, not semiconductor. It's close, the material properties of material are close to metallic. properties. And questions to solve it to calculate the PE and entropy contribution and charge distribution in strontium H13. That should be done in the future. The problem in the PE and entropy contribution is that we need to calculate it for many phases, not only for one phase, for this phase. Otherwise, it will be useless and senseless because we cannot construct a more accurate convex hull using only one phase. We need to calculate all stable phases that we know exist in experiment. Okay, some words about this H5 molecule. I think it's the most interesting feature. Three atomic hydrogen was detected by spectroscopic methods in 20th century, was first predicted by many theorists. And it's interesting that under high pressure, this hydrogen may form even triangle molecules and maybe more exotic molecules that at room condition, at normal pressure, doesn't exist and cannot exist, such as H5 molecule that was investigated in this paper in chemical physics in even 1983. And as I know, the synthesis, the H3 anions were found by Raman spectroscopy and spectroscopic methods in the synthesis of sodium polyhydrides in a sodium hydrogen system in 2016. Yes. So it's probably this is a good candidate to investigate. Is it possible to find how possible the formation of H5 molecule? So this hydride may be a promising candidate for the research in this field. Okay, the second phase is a strontium H22 is almost pure hydrogen with 4% per atomic percent of strontium. Again, I will show this experimental pattern. It's a main phase. Let's say more than 90% of sample content. It's exactly this compound, and it's thermodynamically stable. So in the quiz we should write here the yes, and XRD corresponds to the experiments. Yes, and interesting fact that XRD of hydrogen sublattice has a PCC type, which is the same for phase. As I remember, phase 1 and phase 3 of pure molecular compressed hydrogen, and we can compare also results of calculation of equation of states and the unit cell parameters with the experimental results, and we can see on this diagram, on diagram A, that correspondence is very well actually. And the volume can be very accurate predicted using this structure, so well corresponds to the experimental data. And dynamical calculation within harmonic approximation shows presence of several small imaginary modes, but using the molecular dynamics with machine learning potentials, we calculated the anharmonic phonon density of states and in anharmonic approximation at 100 kelvins, it's actually stable. The structure has the similar X-ray diffraction, the similar cell parameters, and these imaginary modes just disappear because of some distortion in the structure. So within molecular dynamic approach, it's stable, it's dynamically stable and well corresponds to experimental equation of states and unit cell parameters. So it allows us to investigate also and check the band structure of this compound, electronic band structure of this compound, and we used the different functionals, different approaches as LDA, non-conserving, norm-conserving, and TB09, and also we calculated band structure using PBGGA approach, 120 GPa. And you see they are slightly different, but to experimental data, the best agreement with experimental data has exactly TB09 because compound is transparent. Actually, this sample is transparent at such pressure, so it it corresponds that the compound should not be metal, should not be good metal. It should be a semiconductor with pseudo gap. According to the calculation, should be pseudo gap about 1.5 electron volts, and this pseudo gap explains why the color is close to orange of this compound. And yes, TB09 is in the best agreement with the experiments. And at higher pressures, hydrogen H2, hydrogen sublattice, H2 molecules in the strontium H22 aggregates and forms an infinite three-dimensional conductive net, which corresponds to transition from phase 3 of hydrogen, which is insulating phase, to the phase 4 or even phase 5 of the pure hydrogen, which is narrow band semiconductor or even metallic phase, metallic modification. Okay, we also tried to calculate and explain the Raman spectra of these compounds. In experiments, we can observe only one peak, which is almost the same as for pure hydrogen. As I told, the compound is very close to pure hydrogen, just 4% of strontium, and the symmetry is P1, so it's probably randomly distributed atoms. There is a big, okay, it's some kind of maybe randomized structure. And we tried to calculate the test compound, the strontium H2, orthorhombic, as I remember, modification. We tried to calculate it within non-resonant Raman, firstly non-resonant Raman. And after that, we calculated the strontium H22 at temperature 100 kelvins, at pressure 120 GPa. Unfortunately, the results in both cases, the results are not satisfactory. Only a few peaks agree with experimental data. For strontium H2, there are a lot of additional peaks that cannot be found in experiment. And for strontium H22, again, the same situation. There are a lot of peaks, and only one peak more or less correspond to the experimental results. Okay, so this peak was studied in experiment. We studied this sample of strontium H22 at different temperatures, but we were not able to find any additional Raman signals except the Raman signal that corresponds to pure molecular hydrogen. The same calculation were made not only by Abenit code, but also by WASP within the PB functional, and the same results. Actually, there are a lot of peaks, but we understood that non-resonant Raman cannot explain the experimentally observed data, and we should use a resonant approach. But unfortunately, it was a part of Christian Tardini in this project. Unfortunately, at that moment, the calculations are not finished, and I cannot say anything about can we explain the experimental data by resonance Raman, or we cannot explain. So as I told, the experimental data are very close. It's a blue points in this diagram in the bottom right side of this slide. It's a experimental points. It's a blue. And the pure hydrogen, it's a red line or red dots or black lines. So according to different references, a little slightly different. And we saw that actually we are very close to pure hydrogen, just slightly shifting. Okay, so it's a last slide of my presentation. Just a few conclusions I would like to pay attention. Just a few conclusions. So first of all, within this project, we have confirmed the existence of two new compounds. This is strontium hydride monoclinic strontium 3H13 and the P1 pseudotetragonal strontium H22. And we continue work with rest compounds with another concentration of hydrogen. We demonstrated that phase transition and insulator metal transformation in pure molecular hydrogen may be accelerated by low-level strontium doping. And now we can investigate the transformation to metal not at 500 GPa, but at 200 GPa, which is much simpler from technical point of view, from experimental point of view. And strontium H22 can be considered as a low-pressure model of Wigner-Huntington transition in solid hydrogen transition from insulating state to metal state. Again, as I showed in this picture, at 100 GPa, we have only a set of hydrogen molecules somehow distributed within inside of the strontium sublattice, except the tetragonal strontium sublattice. But when we compress it to 200 GPa, these hydrogen molecules aggregates to infinite three-dimensional or some, okay, let's say three-dimensional hydrogen net, which is conductive and demonstrate metallic properties, and even superconductivity of this compound has been calculated. I didn't show it, just. And superconducting TC, critical temperature is about 20 degrees. So hydrogen demonstrates, hydrogen sublattice in this compound demonstrates obvious transition from insulating to metal states, which is also so-called Wigner-Huntington transition in solid hydrogen. Okay, thank you very much for your attention. At this point, I would like to stop my explanations.
Okay, thank you, Dmitry.
30 minutes, almost 30 minutes, so I will not violate the rules.
30 minutes, okay, good. It's with the discussion, actually.
Ah, okay. I thought it's just forever. I'm sorry.
All right, so questions?
I have several questions. Just a clarification first. When you show in slide 6 or slide 10, the comparison between, sorry, no, not 6, perhaps 5. No, okay, 10. Then I'm sure, because at that stage yeah, 10. Yes, the upper corner on the left, you compare the experimental data with theoretical data, but you do not have pure strontium H22 phase, or well, that's what you you hope to compare with. So the experimental ABC are simply taken from the diffraction peaks, the global diffraction peaks, and you have extracted some peaks to show what is the behavior. How are these experimental points generated, actually?
How this experimental points generated?
Yeah.
Okay, we have this the tetragonal strontium H22 pure structure from USPEC search optimized anyway, and after that we can predict X-ray diffraction peaks, and after that there is some procedure which is called the Libelli refinement, which allow us to somehow tune ABC parameters of unit cell predicted theoretically in order to completely explain or completely overlap the experimental profile of diffraction experimental profile. So in this picture, you see that this is red, it's a refinement, and this is the blue line is experiment. It's a diagram A in the top left corner. So you see, we can at least, we cannot maybe completely refine the profile, but we can completely refine the position of peaks.
Yes. So, but this is the experimental data are a combined, a superposition of different phases.
Yes.
That's okay. But so this clarifies the fact that the ABC, yeah, they come from experiment, but not they are not really immediate ABC values. They are kind of extracted. Mm-hmm.
Yes, it's a kind of extraction procedure. Yeah, refinement. But accuracy is not bad, actually. My experience shows that it's quite good accuracy. So Libelli refinement allows us to determine it with, let's say, 7%, so several percent, so even less, within 1%.
Okay, and then you have shown the band structure from TB09, GGA, and LDA. Can you tell a bit more about TB09?
Which details you want to know about this population?
Well, it's you to explain what is this TB09. It's advanced material modeling. So you Can you tell me what is this TD09?
As I know,
why
it's a
is it giving-
functional. It's a functional proposed by. Let me say, I even have some small by Tran and Blacha in 2019 and PRL. So you can see on this picture exactly the formulation of this pseudopotential, not pseudopotential, but functional. And it was proved by the authors that this functional gives much more accurate predictions for the band gap. Compared to PBE or LDA approaches. And the results of the predictions using this method, this approach is close to GW calculations, but computational costs are approximately the same as for LDA and PBE calculation. That's why the people use.
Mm-hmm. And can you tell also about a bit more about the difference between resonant Raman and non-resonant Raman? Why you mentioned that the present result is not satisfactory, but there is some hope to have some other results?
As I can understand, the difference is that in a resonance case, there is interaction of photons with electrons, with electron band structure, because electrons can interact with photons and change their energy and change the position in band structure, just move up or down in the band structure. So this interaction is very complex, and then it changes the intensity of Raman peaks, doesn't change the position, the frequency, the position of Raman peaks, but changes intensity. So we hope that after the full calculation, when this will be completed, when this resonance Raman will be completed, we will see that only one peak, which corresponds to hydrogen, intensity of this peak will be much higher and even like grow, while the rest peaks will just disappear because intensity will be too small due to the interaction.
And in terms of practicalities, what did you do in VASP and Abinit to obtain these results, and what should be done in order to obtain the resonant spectrum? Can you explain the methodology? I mean, this is advanced material modeling, you should know.
I can say that this is very complex, and this is part of Christian Tantardini in this work. And even Christian Tantardini was not able to finish it for 2 months. So I can say that I do not know and cannot answer this question.
Well, okay, for
I address it to Christian.
Yeah, but here you are presenting your own
I know,
project
I completely agree
on AMM on this
yeah,
subject. Okay.
I agree.
Thank you. Thank you.
Thank you very much.
Another question from me.
Thank you, Xavier, for your questions. So I had a few questions. Can you clarify the motivation for studying exactly this system? Why strontium?
Okay. Why strontium? Let me just explain. This is some kind of the question related to background to this research. The first hydride that was studied experimentally was sulfur hydride. After that, the people, because of its outstanding superconducting properties. After that, motivated by this idea to find a new superconductors, so people studied a lot of other covalent hydrides. Tin hydride, phosphorus, selenium hydrides, and so on. It was found that none of those hydrides demonstrate so high critical temperatures and need to change some. And the people went to the hydrides of metals. It was predicted that lanthanum, yttrium hydrides should demonstrate even higher TC, higher superconducting properties, and actually it was confirmed. Just a couple of years ago, it was confirmed that lanthanum H10 has 250 kelvins critical temperature superconductivity, and the people start to search how can we improve it. Maybe use a different metal. It was found that actually the metals with more d electrons, with larger number of d electrons, like D2, D3, iron, tungsten, tantal, and all of other metals, they do not form superhydrides. They do not have interesting chemistry with polyhydrides. But metals with less number of d electrons, let's say D0 with S2 electrons like strontium, barium, calcium, are the most interesting compounds that they form always, even at low pressures. They form superhydrides, polyhydrides with big content of hydrogen. So the strontium just the next step. Barium we already investigated, published in Nature Communications. Calcium is very complex for synchrotron research because of very scattering factor of X-ray diffraction of calcium is very low. And strontium something intermediate that can be measured and at the same time quite easy to calculate.
Okay, I see. Thank you. So the other question is about the temperature. You mentioned different temperatures, but so what temperatures were experiments done at?
Room temperature, 300 Kelvin. For Raman studies, down to maybe 40 kelvins. So it's from 300 to 40 kelvins.
I see. But these materials were prepared at room temperature.
They studied at room temperature, but synthesized at much higher temperature during the laser heating procedure. The temperature may reach maybe 1,000, 2,000 kelvins. So
I see.
Yeah, we think.
So my question is then, does the result, I mean, did they repeat the experiment? Did they repeat the experiment several times and the result was the same? Does it depend on the path of how you go, like reduce the pressure, I mean, increase the pressure, or does it?
Results, let's say experiments were repeated many times, about 7 times, 7 diamond cells. And each cell has a little bit, not little bit, let's say only a few cells demonstrate the similar results, similar X-ray diffraction patterns, because always we cannot control hydrogen content. It's always different. So that's why in some cells we can reach the strontium H22 because enough hydrogen. In some cases, some cells it's not enough, and we synthesize just strontium 4 H46. Strontium 8 H46, something like that. So close to 4, 5, 6. In some cells, it's close to 9. So it's uncontrollable. It's not controlled hydrogen content.
Okay. Did you consider a spin, or it doesn't matter in this?
No, it doesn't matter at all. Magnetization, total magnetization of all compounds are 0.
So is it confirmed experimentally, or?
It cannot be confirmed experimentally because magnetic measurements in diamond analysis are very complicated, and just a few cases in just a few experiments.
So this is the theoretical conclusion.
It's a theoretical, pure theoretical. Yes.
Okay. So you tried different spins and you didn't find that it's
yes, of course.
Okay.
Yeah, we tried spin polarized.
I see. Okay. And what do you think about, could quantum effects for hydrogen affect the properties and the spectra and everything? Did you try to include them?
You mean ZPE, zero final motion?
No, the quantum nuclei.
Can you please explain a little bit more? Which
ZPE is part of it, but in principle, you have finite temperature. So there is maybe tunneling and kind of changes in the structure.
Absolutely agree. It's future work because as I showed, there are several phases. We now determined only 2 phases. We're sure that this is strontium H22, and here in this position of the diagram, equation of states, volume pressure diagram, it's this strontium 3 H13, but the rest compounds are not completely determined. So we cannot construct a accurate convex hull with accounting the entropy, with temperature factor, with accounting the PE. We need to have all set of structures, and after that we will calculate the PE for all structures, and we'll compare all together. Because now we can, of course, quite easy to calculate it, but it's useless, quite useless.
Okay. Okay, I see. Thank you, Dmitry. We have to move on. It's time.
Maybe I have to add. Dmitry, is this part of your future PhD presentation, PhD defense presentation?
Probably no, because the PhD presentation, we negotiated it with Alexei Buchachenko, and he agrees that I can do PhD defense, PhD thesis based on my publication, previous 5 publications. This work is a future publication, so I will not include it in the thesis.
Okay, so then I have only one comment. So on official presentations, you should not use informal words like rubbish papers or garbage cans. So please do not use in official presentation this word.
Absolutely agree, Andy. Absolutely agree.
Well, I also wanted to comment on that. They are also not rubbish, in fact. They are just part of research, right? People first have to explore. Otherwise, you stand how Newton standed on the shoulders of giants, right? You know that they are rubbish because they are done. Otherwise, you would never know. So this is also unfair. Okay.
Okay, agree, Sergey.
Okay, good.
My mistake.
So next person, Maria, who is next?
Yeah.